Hi, it's time for another math easy solution. Today we're going to discuss further into differential equations, but now look at linear differential equations or first order linear differential equations and go over the derivation for the solution of these types of differential equations. Basically, a first order differential equation is one that could be put in the form of dy over dx. So there's your derivative. And it's first order because we're only dealing with the first derivative. And then we have p of x, so a function of x times it by y equals 2 q of x, another function of x, like that. And it's linear because this y, there's no square in it, it's just linear differential equation like that. Yeah, so we have the function y, and then we also have the derivative. That's why it's a differential equation, but there's no y squared and there's no second derivative for, so that's why it's first order, and this is why it's linear. So that now that we have this, let's move further. Basically where p and q in this equation are continuous functions of x on a given interval. So this type of equation occurs frequently in various sciences, as we will see in later videos, so stay tuned for those. Then basically an example of a linear equation is, for example, if you have something, let's say x times y prime plus y equals 2x, like here. And now this is a linear equation because, well, you could just sort this out. There's a y prime, and then it doesn't look exactly like this, but we can, well, divide both sides by x. So if we do that, what we end up getting is, well, this x cancels, so we get a y prime plus, and then we have this 1 over x times y, and on the right side is just 2x divided by x, that's just 2. So this looks exactly like this. This q of x could be equal to 2, p of x is equals to 1 over x, and then there's our dy over dx, which is just y prime, and there's our y. So that's how it looks like. And now what we want to notice is basically from this equation, notice that this differential equation is not separable because it's impossible to factor the expression for y prime as a function of x times a function of y. So recall my earlier videos on separable equations. Make sure to watch those. I'll put the link below. Basically, we can't write this in that form, so we can't just integrate it in the methods we did before. For example, if you want to rearrange this to make this just y prime by itself, what we get is, move this on the other side, y prime equals to 2 minus, this is y over x. Now if you want to separate these so that it's a function of x times a function of y, i.e. f of x times it by g of y, so that's what we want this right side equals to, so y prime. So this is what we want, and then we can divide this over and then integrate, etc. But here, notice we can't really do that. So if we try to do something like this, we'll just multiply this to get rid of this x in the denominator. We'll do multiply by x divided by x and then move this x inside. So we get equals to 2x minus, and then the x cancels, minus y, times it by, and then this is our 1 over x. So what we end up having is this is a function of x and y, and then this is a multiplication by a function of x, like here. So this is not a separable equation. But even though we can't solve this by the methods of the separable equation, we can still solve the equation by first noticing by the product rule. So if we notice this equation here for this example, before this one, so if you notice this left side here, this xy prime plus y, if we notice that by the product rule, if we look at the derivative d over dx of xy, so if we look at this function together, the multiplication of these, or in other words, the same way as writing xy prime, just state as the derivative. So if we're taking the derivative of these two by the product rule, the derivative of x is just 1. 1 then times by y, but first we'll do the derivative of y. So derivative of y, so we'll have the x y prime, then plus the product rule, derivative of x is 1, and then we just add the y there. So notice here this derivative of xy prime, or the derivative of xy is equal to xy prime plus y, which is 2x. So this equals 2x. In other words, what we get is xy prime is equal to 2x. And now this is a separable equation. So we'll write that down. This, or I'll just write it as a separable equation. Separable equation. I'll just write separable. And the reason is, let's leave that out of there, is because, well, just look at this one. It's the same thing as writing dxy. Write that a bit neater. dxy over dx. This is the derivative equals to 2x. So we can move this dx onto this side. So we have all the y's on one side and all the xy's on the one side and all the dx or all the x's on the other side. So in other words, we have dxy like this equals to 2x dx. So now all the x's are on one side, all the xy are on the other side. So it's separable. Instead of separating x and y, we separate xy and x's. So now we just take the integral on both sides. So when we do that, we end up getting, and I'll just move this a bit neater here. Whoops. Yeah, just move that over there. So like that. So then the integral of dxy is just, well, xy. And then we have to add a constant c1, or the integration constant, we'll call that c1 because we'll have another one here. And then the integral of this is, well, 2. Integral of x is x squared divided by 2, so those will cancel, plus a constant of integration, we'll call that c2. So these cancel, and what we're left with is xy equals 2x squared. Now move this onto the other side, plus c, where, and I'll just write this, I'll just write it over here, where c is equal to c2 minus c1. So just subtraction, and this is just a constant. Subtraction of constants is still a constant. So now that we have this, we can just divide by x on both sides. Just divide by x like that, so that we can cancel all this, and we get y of x, just a function of x, is equal to, and then x squared divided by x is just x, plus c over x. So there is our solution to this differential equation, or to this linear differential equation. So that's just a quick example of it. Yeah, so that's a quick example, but what I'll show in this video is that this works for basically in the general for any linear function, and linear equation, differential equation. And also I want to state here, so if we had been given the differential equation in the form of equation 2, and I'll write these out. So this one we'll call this equation 1. And then this one here, we'll call this equation 2, like this. And this one's here. So if we were given this equation as opposed to this one, because remember we were looking at derivative of xy equals xy prime plus y. So what we'll have to do here is just multiply both sides by x first. So we would have had to take the preliminary step of multiplying each side of the equation by x. In other words, if we had if we were given equation 2, so y prime is equal to 1 over xy equals to 2. So then what we'll have to do is multiply both sides by x. Like that. So when we do that, then we end up getting, well, this xy prime plus y, those cancel, equals to 2x. And then we can go ahead and realize that this is actually xy prime. That's this xy prime plus y. So what actually ends up turning out is that it turns out that every first order linear differential equation can be solved in a similar fashion to this example we did by multiplying each sides of equation 1, which was the very first equation here. Write that 1. So if we multiply both sides by a function, and we'll call this function, by a suitable function I of x, just function of x, and this is called an integrating factor. So basically, we can multiply any differential equation by I of x, and then following similar fashion, and then solving for that the function in the differential equation. So and in this case here, if we had a differential equation like this, this one would be our I of x. So this would be I of x in this case. So we multiply both sides by this function I of x. So we try to find I so that the left side of the equation, when multiplied by the I of x, becomes the product of it becomes the derivative of the product of I of x times y. So in other words, we're multiplying this so that what we can eventually get is this, which is the product of the two. And in this case, that's x is I of x. So that's what we want to get, and then from there we're basically creating a separable equation. So if we start off with equation 1, which was simply dy over dx plus p of xy equals to q of x. So let me just see if I wrote this right. Yeah, so if we start off from this one, dy over dx plus p of xy equals to q of x. So we start off from there. And this one, I'll just simplify this and write this as y prime. So what we want is we want a function when we multiply so that the left side, so when multiplied by I of x, we get I of x, and then we multiply this whole thing on the left side, y prime plus p of xy equals to the derivative I of x times it by y. So the derivative of this product of I and y. Yeah, so what I'll do is I'll circle this and I'll call this equation 3 because later on in the video I will reference this equation. So what we end up having is thus this I of x y prime, or the derivative of the product, is going to be equal to I of x times q of x. That's just because we're multiplying both sides of this by I, and this part right here is simply q of x. Because remember, y prime plus p of x times y is equal to q of x. So this is just q of x. So then this whole thing here is just I times q. So that's what we have right there. And again, writing this in a different notation like this, di, or I'll write that afterwards here actually, just simplified further. This is the same thing as writing di, I'll just diy. I'll remove the x just to make it easier, because remember, everything is a function of x, and y is a function of x as well. So diy over dx is equal to iq. And again, I just save time just removing that x, making it a bit neater. Then move the dx on the other side, so as you can see, it's separable once we remove them all. We get diy equals to iq dx, and now we just take the integral both sides, because we've separated all the x's on the one side and all the I and y multiplications on the other side. Yeah, so now the integral of this left side is going to be, well, just I times y, and then always add a constant of integration. We'll call this c1, and this equals to, on the right side, just iq dx, so we'll have to solve that. And I'll move this over to this side, and then also divide both sides by I, so that we can get rid of this I in front, so we'll eventually move it over there. So what we'll end up finally getting is we get y of x is equal to, then this is going to be dividing by it, but first I'll just write that down just to make it a bit easier. So what we get is iy, equals to, I'll write that down after just to get rid of the c there, to make it a bit neater, iq dx plus c, where, I'll just write that over here, where, again, c is going to be, in this case we're just moving it over, so c equals to negative c1, which is a negative constant is still a constant. And you don't know if it's negative c1, it could be positive, etc. I just did this just for completeness. So now that we have this, we divide by I in both sides, or just do this, divide by I both sides. So what we end up getting is thus, y of x as a function of x is equal to 1 over I of x, and now we're dividing out by everything including c with a constant, so we get overall the integral I of x, put this here for completeness, times q of x times dx plus c, and there it is. And this is the general solution. Yeah, this is the general solution of the first order linear differential equation, and I'll write this as equation 4 because I'll reference this later on. Yeah, so now to find such an I function or integrating factor, we can expand equation 3 and cancel terms. So let's go back to equation 3 where I referenced it. That's this one right over here. I of x times y prime plus p of x times y, and then because this is what we want, so remember that. So we want this function such that when we multiply the left side, it equals to the product, the derivative of the product of I and y. So let's write this down. So let's scroll this over here. So let's write this as I of x times it by y prime plus p of x times y equals 2. So again, we want I of x, y prime, and not y prime, y, and then y prime. Yeah, so first thing is we expand this, but we could do that by multiplying this inside. So notice what happens when we multiply I of x and then multiply it inside, we get, and then I'll just remove the x just to make it neater. So I times y prime plus I p y, and then the right side equals 2. Now the derivative of this is going to be, this is going to be I prime and then y, and then plus we have right here plus just I by using the product rule, and then y prime. So that we have this, but notice the like terms here. I and y prime cancels with I and y prime on the right side. And so what we're left with is over here I, p, y, and I prime and y like that. But also notice what happens is y, these ones can cancel out as well. Once you cancel those out, divide both sides by y, those cancel. So what we're left with is I prime equals 2 I p. And then what we can do is move the y on this side. So now we have a differential equation. So remove the I onto this left side. So what we get is this I prime over I is equal to p. And I'll just make it easier like this. So now we can take the integral of both sides. Well, before I do that, what I'll do is just write this as this. This is going to be 1 over I, and then this I prime, same thing as writing di over dx right here, because it's a function of x inside. So this derivative is like that. This equals to p, and then we can move this over to the other side. So we're separating all the x's on one side and all of the i's or I of x on the other side. So what we get now is di over I is equal to p times dx, or p of x times dx. And then we can integrate both sides, and now that it's separated, integrated, and recall that the integral of 1 over I or 1 over x, etc. is going to be ln of absolute value of that value. So this is ln of absolute value of I, and then always add the constant of integration c1, and now this equals 2. On the right side, we'll just leave this as p dx, integral of p dx, and then the next thing we'll do is move this over to this side, and then what we get is ln absolute value of I equals to, just move it over, and this equals to integral, make this bigger, integral p of dx, and then what we'll do is write this as c, where just for completeness sake, where c is equal to negative c1, we just move it over. So the c1 is not the same as before, this is just a generic constant of integration, and this is again a constant. Negative of a constant is still a constant. So now what we'll do is to get rid of this ln, we again recall, we just take the power of, make them both power of e, do that to both sides, so we're not changing anything. And now this cancels based on the logarithmic property of it, and now this e and ln cancels. We're left with absolute value of I is equal to, and then this one we could use power rules of moving this. Whenever you have an addition in the power, you can separate that with a multiplication with the same base. So e to the c times e to the integral of p dx. And now remove the absolute value sign. Recall absolute value is the same thing as writing plus or minus. So the inside could be plus or minus. but then you're still gonna, all you're doing is making it positive with the absolute value sign. So the inside could be whatever, plus or minus e to the c, e to the integral p dx. So now what we have now, if we simplify this and make this called a, so we get I equals to a, or let's write this as I of x equals to a e to the integral of p of x dx for completeness. So this is the general solution for it, where what we have here is a is simply equal to plus or minus, a is equal to plus or minus e to the c, where this is still a constant, because c is a constant, e to the power of it is still a constant, and then you plus or minus of a constant is still a constant. So that's just a constant. But now, this is a general solution for the integrating factor I. I'll move this down. Basically, note that we are looking for a particular integrating factor. We don't need to get an infinite number of them. We just want one, not the most general one. So we could take a equals to 1 and use the following integrating factor. Yeah, so if we get a is equal to 1, so then we'll have I of x is equal to, a is 1, e to the integral of p of x dx. So that's all we need to find. Yeah, so basically we've just solved everything we need to do for solving the first order linear differential equation. And now to basically summarize everything that I've just derived here, the general solution of the first order linear differential equation, so this one here, write this bit neater, dy over dx plus p of x times y equals to q of x is given by the formula that I solved above. Y of x equals to 1 divided by I of x, where that's an integrating factor, and then times it by the integral of I of x times q of x times then dx plus constant c, where the particular solution of it, not the general, just the particular solution, because we only want one, of integrating factor is I of x equals to e to the power of p of x dx. And in later videos I'll go over some examples which will make it more clear why we only need one particular solution as opposed to a general one, and so stay tuned for that. But instead of memorizing all this formula, it's actually easier to just remember the form of the integrating factor here, e to the power of p of x dx. So in other words, to solve the linear differential equation, y prime plus p of x y equals to q of x, to solve this we just multiply both sides by an integrating factor I of x equals to e to the integral of p of x, which is this one over there, dx, and integrate both sides. So it's better to memorize this than this entire formula above here. So this is what we'll memorize, and I'll do this in later videos and will look more clear once I go over some more examples. So basically, instead of memorizing all this, all you got to do is first get the differential equation into this form, and then you know your p of x, and then multiply both sides by integrating factor I, and integrate both sides like you would any separable equation. Anyways, that's all for today. Hopefully you'll learn, and like always, you can download these exact notes. Hopefully you enjoyed this pretty extensive example, and I'll put the links to the notes below like always. Anyways, that's all for today. If you learn, and stay tuned for another Math Easy solution.